Hey everyone, and welcome. Today we're going to pull back the curtain on one of the most important ideas in all of modern software, object-oriented programming. You might hear it called OOP. If you've ever looked at a complex app on your phone and wondered, how on earth did they build that? Well, a huge part of the answer is right here.
So think about this. For the longest time, one of the biggest challenges in coding was this: gap. The gap between how we humans see the world, full of things, objects, and how computers work, which was all about pure logic and functions. How do you actually explain what a car or a bank account is to a machine?
And then came the answer that pretty much changed everything. OOP. Instead of writing code as one giant, long to-do list, OOP flipped the whole idea on its head. It said, let's build our software to mirror the real world. Let's create these little self-contained objects that know things and can do things. Okay, so how do we actually make these objects? Well, you can't just start building, right? Just like if you were building a house, you'd need a plan first, a blueprint. In the world of OOP, that blueprint has a special name. It's called a class.
And this is the key idea right here. A class itself isn't something you can, touch or use. It's just a definition. It describes what a car is supposed to be. It says a car should have properties, like a brand and a color, and it should have behaviors, like being able to accelerate. But the blueprint itself, it's not a car you can actually drive.
And here's what that looks like in actual code. See? We have our car class. It clearly lays out that any car we create from this blueprint is going to have a brand and a color. Those are its properties, or its data, and it's going to have the ability to accelerate. That's its behavior, or its method.
All right, we've got our blueprint. Now for the fun part. It's time to actually build something with it. This is where we go from the abstract idea of a class to the concrete, real thing, an object.
An object is what we call an instance of a class. It's the real deal. Using that one car blueprint, we can now stamp out as many individual, unique cars as we want. A blue Ford, a red Toyota, a black Honda, all from the same single plan.
And look at the code. See that little word new? That's basically the magic word. It's the command that says, hey computer, grab that car blueprint and build me a real one right now. Then we give it its own specific details. And just like that, my car is a real thing, an actual object in the computer's memory, a red Toyota.
So let's just nail this down. On the left, the class. That's the idea, the recipe, the blueprint. On the right, the object. That's the actual car you built, the thing that exists and takes up space. It's as simple as that. The blueprint versus the real thing.
Okay, so now we can imagine having all these different objects in our program, all interacting with each other. But you can see how, in a really big, complex system, that could get messy. I mean, really chaotic, fast. We need a way to keep things organized and safe. And that brings us to our next big idea: encapsulation.
I mean, seriously, think about it. Imagine a banking application. If any random part of the code could just reach in and change the balance of a bank account with no rules or checks, well, that would be a complete disaster. So how do we stop that from happening?
The solution is just brilliant. You bundle an object's important data together with the specific methods that are allowed to change that data. You wrap it all up into a single protected unit. It's literally like putting a protective bubble around the object's core information, making sure nobody can mess with it except in very specific, controlled ways. This bank account example is perfect. See that word private right next to balance? That's the protective bubble. It means nothing outside of this bank account object can directly see or change the balance. The only way to add money is to use the public deposit method. And that method has rules. It checks to make sure the amount is positive. That's control. That's safety.
And these keywords, things like private and public, are called access modifiers. They're the tools programmers use to enforce this encapsulation. As you can see in this table, they give you really fine-grained control over who gets to see what, from private, which is super restrictive, all the way to public, which is open to everyone. It's all about managing access.
All right, on to our last major pillar of OOP. And honestly, this one might be the most powerful when it comes to writing code efficiently. It's called inheritance, and it's all about letting our classes form relationships with each other.
The best way to think about it is like a family tree. You can create a very general parent class, let's say animal, and in that class, you define behaviors that all animals share, like eating and sleeping.
Then you can create more specific child classes, like dog, cat, or bird, that inherit everything from the animal class automatically. They get the eat and sleep methods for free. Then they can add their own special skills, like bark or meow. Think about it, you only have to write the code for eat one time, instead of for every single animal. It's a game changer.
And, these family trees can have different shapes. The most common is single inheritance, which is just a direct parent-to-child link. But you can also create chains, which we call multi-level inheritance. So you might have a poodle class that inherits from dog, which in turn inherits from animal.
So after all that, why does this matter so much? It's because these three big ideas, classes and objects, encapsulation and inheritance, all work together to solve that original problem. OOP gives us code that's beautifully organized around ideas we already understand. It makes our code incredibly reusable, so we're not constantly reinventing the wheel. And it makes huge, complex systems so much easier to build, manage, and keep secure.
In the end, object-oriented programming gave us a way to bring order to the chaos of code by modeling the world we already know. And that leaves us with one last, really fascinating question to think about. As we move forward building things like virtual realities, advanced AI, and massive simulations, what happens when we use these very same principles to start modeling worlds that we've only just begun to imagine?